Welcome to Module 4, and in this module we will be exploring the different equipment and software that is used in exoplanet observing. So let's take a look at what a typical setup might be. This is a backyard telescope in suburban Annapolis, Maryland. And what we see are the various components of what a typical amateur astronomer setup would be. This, by the way, this equipment is very similar to amateur astronomer equipment having to do with deep sky imaging or planetary imaging. We see, of course, the telescope itself, a mount that the telescope is mounted on. We'll see in a little bit some of the important characteristics of the mount. We see a camera, in this case a monochrome CCD camera, which is the preferred type of camera as opposed to a color camera, and that's so that we can use different types of filters that you see here in a filter wheel. Here we see a guide camera that will pick off the light of a star in the field of view that the CCD camera is viewing, and that's important for auto guiding, again, that we'll talk about later. Optionally, we see an active optics unit here, which is used to take care of even more precise guiding than what a typical off-axis guider is used for. And we see here that in this particular setup, the controls are run indoors. It's mounted on a concrete pier so that there doesn't need to be polar alignment for every observing session. Some telescope setups are more portable, where they're not on a concrete pier. Some don't have quite the sophistication as this does. Some may not have an active optics unit, for example. But certainly the minimum for exoplanet observing would be the telescope itself, a mount that is fairly good in terms of low periodic error, being well balanced, and so on. And also a monochrome CCD camera with a filter wheel and a auto guiding setup. Some amateur astronomers have actually successfully done exoplanet observing with scopes as small as 8-inch aperture. This particular telescope setup, for example, is an 11-inch aperture telescope. So let's take a look at some of the characteristics of CCD camera itself. If you recall, we said that electrons are converted to digital counts. The term gain refers to the ratio of electrons to ADUs. So if one has a certain number of ADUs, one can multiply the gain by that count to get the number of electrons that those ADU counts represent. Typically, with every CCD camera, as the image is read out, there's a certain amount of noise that's measured in terms of electrons. There's also a certain amount of background noise referred to as dark current, which is a function of the number of electrons per pixel per second. So the longer the exposure, that's to say the longer number of seconds, technically there would be a larger amount of dark current.
Now, strictly speaking, dark current is the rate at which electrons accumulate in a CCD well due to thermal energy. But we will also use the term dark current here to also mean the amount of electrons and therefore ADUs that have accumulated over a given exposure time.
The read noise and the dark current are a couple of the factors that we need to consider when we're calibrating our images to eliminate those sources of noise. Certainly a CCD camera characteristic are the size of pixels. These are often noted in microns. The number of pixels both in the X and the Y direction on the CCD detector. And as we discussed previously in the previous module, the quantum efficiency of the CCD detector. So these are 6 characteristics that define a CCD camera that it is important for you as the exoplanet observer to know and understand. Now, let's talk about the sources of signals and noise into our CCD detector. As far as signals are concerned, certainly the photons that enter the CCD detector are very important sources of signal. These are, as we said earlier, translated to ADU counts. Dark current actually is an unwanted signal. And as we said earlier, that's a function of exposure time. There's another type of noise that is just a constant offset to our ADU counts when we read an image from the CCD detector. And even though we say it's noise, it's actually a signal that needs to be eliminated. And that term is called bias. Now, examples of noise. Noise actually here refers to the uncertainty that is in a CCD image. And so the causes of uncertainty are three. One called shot noise, which is just the uncertainty of a photon count. So if we're looking at a star from image to image, just by the nature of photons getting dispersed in various ways, over a certain period of time, we may not always get the same count. And so that uncertainty is referred to as shot noise. There's also uncertainty in the dark current itself, and there's also uncertainty in the read noise. So these three contributions of noise accumulate to the amount of uncertainty in our signal. So the key here, of course, is to increase the signal and reduce the noise. And I'm sure you've heard the term signal to noise ratio, which is a measure of the signals to the uncertainty, that's to say, to the noise. Now, turning to the telescope itself, that's to say the optical tube, there's certainly, as I'm sure you know, different types of optical tube assemblies. Schmidt-Cassegrain is what we saw earlier in the example setup. There are reflectors, there are refractors, and so on. All of these different types of optical tube assemblies are possible to be able to use for exoplanet observing. The aperture or the size of the opening of the telescope itself is an important characteristic. The focal length of the telescope, any central obstructions on the optical tube assembly. For example, on a Schmidt-Cassegrain telescope, there's a secondary mirror that takes away some of the light collection from the aperture. The thermal characteristics of the telescope is important to understand because that may introduce some variability and noise into our computations. The accuracy of focusing, and we'll say a little bit more about the focusing having to do with exoplanet observing, where it doesn't need to be as critical, for example, as if we were doing deep sky imaging. The collimation of the optical tube assembly, that is to say, bringing to as fine a point as possible the focus of an image, and the spherical aberration of a telescope, again, having to do more with the telescope's ability to have a very well-defined image across the diameter of the aperture so that there's not different focus points on different parts of the aperture. Now, as far as the characteristics of an image itself, one important measure of our ability to resolve certain parts of an image has to do with image scale. Image scale is measured in arc seconds and per pixel. That's to say the width of an image that a given pixel is able to collect photons on. And that's given by the formula 206.265 times the pixel size in microns divided by the focal length in millimeters. So for example, a pixel size, a image scale of 4.5 arc seconds per pixel would say that a given pixel is able to collect photons across a range of 4.5 arc seconds. Now, if we combine the image scale of all of the pixels, then we're able to compute the overall field of view that the CCD detector is able to observe. So if we multiply the image scale by the number of pixels, then we'll see a certain field of view. For example, a field of view for an 11-inch telescope with a 4.5 4.5 arc second image scale, depending on the binning, let's say it's 2 by 2 binning, one might be able to achieve a field of view of about 14 by 12 arc minutes. It turns out that binning actually is not does not affect the field of view. It's more a function of the image scale of pixel unbinned times the number of pixels. Now, another set of characteristics that have to do with the mount itself has to, first of all, to do with the type of mount. There's German equatorial mounts, fork mounts, alt-az mounts. And each of these mounts have different pros and cons with respect to exoplanet observing. A German equatorial mount, for example, would require a meridian flip to occur as the planetary system that one is observing passes above the local meridian. And so there could be some loss of observing time in that respect, having to get back on target. A fork mount is much more optimal for exoplanet observing in that it's able to track across the meridian. However, having said that, there are some possibilities that we use in software for correcting any change on the detector that occurs as a result of a meridian flip, where the planetary system, the star and its planet, all of a sudden moves to a different part of a detector. There are ways in software, as we'll see, for making some corrections of that effect. Each mount generally has a certain amount of periodic error, primarily in the right ascension direction. This is a function of the worm gear moving the ring gear, and in some cases, if there's little glitches in the worm movement or on the ring gear itself, there may be some error introduced as one is tracking and doing guiding. However, these errors often can be compensated for by some mounts that allow for periodic error correction, or in fact can be compensated for in guiding. Deck backlash has to do with the errors that might be introduced in moving from north to south and south to north in the deck direction. Generally, there are no changes in deck direction, only changes in right ascension. So where deck backlash might come into play is if one is moving the mount to a new location, and the mount might not put the image dead on center because of some backlash in the deck direction. Balancing of the mount is important for auto guiding, and so a well-balanced mount certainly is important. And finally, having an accurate polar alignment is important, because if a mount is not accurately polar aligned, there could be some long-term drift
in the deck and RA directions.
This can be compensated for often. This can often be compensated for in auto guiding, but it's really best to have the mount accurately polar aligned as much as possible before beginning the observation. Now, the image chain that is involved in doing exoplanet observing has some fundamental parts and some optional parts. If one wanted to increase the field of view, one could put a focal reducer in line between the star and the detector. As is possible to put a rotator in line. This would be useful, for example, if one is trying to rotate an off-axis guider to get a good guide star. As we said earlier, an active optics unit is optional, but probably more than anything, what's important is an off-axis guider, as we see here, which consists of a pick-off mirror that will pick off light coming through the imaging chain, will go to a separate auto guide camera, feed into software on a computer that will then feed back to the mount to change the rate of right ascension,
maybe deck direction,
to keep a guide star centered and therefore to keep the target centered. So an off-axis guider, I would say, is definitely preferable than, let's say, using a guide scope with a guide camera. A filter wheel to allow different filters to be used is not mandatory, because one could always put a filter, let's say, on the front of the CCD camera, but certainly very flexible in terms of being able to change filters between observing sessions. And of course, the CCD camera itself. Now, we said a lot about auto guiding in the last couple of slides, and I think it's important to spend a little bit more time about it, since it is so critical for exoplanet observing. As we alluded to, one could use a separate guide scope for auto guiding. One of the cons of using a separate guide scope is that this could result in flexure between the guide scope itself and the main optical tube. So it's not the ideal approach for doing auto guiding, but certainly it has been used in the past. The ideal approaches would be off-axis guiding, as we just described, with a pick-off mirror. There are some CCD cameras that have a guide chip on the camera, and there's now an approach for doing on-axis guiding, where the guide star is actually within the same field of view as the main imaging camera. All of these approaches, however, should be using a fairly sensitive guide camera for a couple of reasons. One is to be able to easily obtain a guide star, but also because of those who might have a German equatorial mount, where a meridian flip would occur, let's say, during the observing session, one would not land on the same guide star that was used prior to the flip. And that means that a fainter guide star might have to be picked up by the guide camera. So having a sensitive guide camera is important for that reason as well. Ideally, the guiding to the mount itself, if not to an active optics unit, should be done with an ASCOM pulse guiding approach. And there's several advantages to doing pulse guiding via standard ASCOM communication protocol, and that would be the preferred approach for mount control. And finally, there's a number of different auto guiding software products. Each requires some initial calibration to obtain the relationship between the guide camera and the RA and deck directions, so that any corrections that are going to be made to the mount can be computed from the orientation of the guide camera. Some auto guiding software will automatically correct for changes in declination, as well as to the side of the pier. So that would alleviate the observer from having to recalibrate or do any kind of manual deck calibration changes. And finally, some of the more popular auto guiding software products that are out there are PhD2, the Software Bisque SkyX Pro product, and maximum DL. Now, because timing is very important when it comes to exoplanet observations, let's spend a few minutes talking about how to get accurate timing for our exoplanet observations. If we consider the light of a star, for example, coming down to an observer on Earth, one would measure a certain time when those photons arrived from that star. Now, let's suppose that we call that time period time A. Now, let's assume 6 months later, the Earth is on the other side of the sun, and therefore it's at, let's say, a shorter distance to the star. Then the time of the photons arriving from the star to the Earth is going to be slightly different. So depending upon where we're measuring the light, there could be a difference in time for arrival of photons, and therefore, in terms of doing predictions, it might be complicated as to when a transit might be taking place or is being recorded. Now, let's further complicate the issue by assuming that we're in the middle of the sun, noted by distance c. Well, that also is a different distance from the star, and an observer on the sun would also time the arrival of those photons slightly differently. So one might say, well, let's focus on having the center of the sun as our reference location. Well, that's even not quite accurate, because the center of the solar system actually is not in the center of the sun, but it's a place called the barycenter, which is a little bit further from the center of the sun. And so what scientists do is they use the barycenter as their point of reference. So in terms of doing exoplanet observations, to be very accurate, as we'll see in a minute, it's the barycenter that will be our reference location for exoplanet observation timings. So if we were to say, what time is it? Based on what we just saw, it's a function of really what's the reference location where we're measuring the time. And also, it's a function of what clock we're using. If we're using a watch, it may not be as accurate, for example, as an atomic clock. So the two factors, where we are measuring something from and what is the clock or time standard we're using, is called the time base of our measurement. And this will vary across different types of observations that are taking place. But it's important that we standardize what our time base is, so that when we're comparing one observation to another, we're consistent in our measurements. So let's say that local time in San Diego on October 29th, let's say it's currently at 1300. The equivalent universal time in Greenwich, England, if at this time of the year we're 7 hours behind, the Greenwich time, universal coordinated time, would be 2000 on October 29th. However, let's convert that to Julian calendar date. And so the Julian calendar date would be, as you see here, 245-7691.3333. So this would be the Julian date of the universal time of this particular observation. But as we saw earlier, that depending upon the location of the Earth in its orbit and the distance from the star being able to change, we need to get a little bit more accurate than just even universal time. Well, some observations are done in a time frame where the reference location is the sun, and this is called a heliocentric Julian date. And in order to compute the heliocentric Julian date, using as an example a particular star, Kelt 1 in this case, at a certain RA and DEC position, we get a different Julian date because, again, It's as if we're observing from the sun as opposed to the Earth. That difference, believe it or not, is about 6.4 minutes. So getting a little bit more accurate, independent of our reference location on Earth and its location in the orbit, we can talk about using a heliocentric Julian date. But that's not even quite accurate because, as we said, the very center of our solar system is a little bit different from the center of the sun. We call the reference location of the barycenter BJD TDB, barycentric Julian date, barycentric dynamical time. In the case of Kelt 1, for example, we would use not only the RA and DEC location of Kelt 1, but in this case also our latitude and longitude. Let's say we're located at roughly 32 degrees north, 116 degrees west, at an altitude of 1,131 meters. Those two combinations of our location and the location of the star are what are used to derive BJD TDB. In the case of this particular sample observation, we come up with a BJD TDB date, as you see it here. It turns out that's a difference of about 1.1 minutes from the heliocentric Julian date. So the point of all of this is that it's important to know what time base we're using for the predictions that we're trying to obtain our transits of, and also in terms of recording our results. We want to make sure that we're using the appropriate time base. Now, for scientific purposes, nowadays the preferred time base is BJD TDB, which eliminates any dependency on where we are on Earth, where Earth is in its orbit, and even, in fact, goes beyond even measurement as if we're in the middle of the sun. It computes as if we're in the very center of the solar system. So that's the preferred measurement we'll be using in our examples, BJD TDB, in fact, as our time base. Now, in measuring exoplanet observations, it's important to capture time very accurately, especially for scientific purposes. Most computers do have their clocks drift. So we need to periodically update the computer clock on the computer that's being used for the image capture. And we do that by synchronizing it with the atomic clock. There's freeware to do this. One in particular is a program called Dimension 4 that has a very user-friendly interface that one can define the Internet time server, in this case from the US Naval Observatory, the frequency of updates, and this particular program then running in the background will periodically update the computer clock. It's important that we do this during our exoplanet observing session so that the timestamps on the images are as accurate as possible. One of the outputs of Dimension 4, as you see here, for example, are the corrections that are made over a certain period of time. So for example, in this case from July 18th of 2016 to September 26, 2016, there were errors that need to be corrected plus or minus a second. And that accuracy, again, needs to be corrected, especially if we're doing image capture for scientific reasons. Now let's turn to how amateur astronomers create light curves. You saw earlier in one of the beginning modules the importance of light curves. The way we do that is we select a number of stars called comparison stars in the same field of view as the host star that we're interested in. And we use these comparison stars to help eliminate some common events that would result in photons, for example, being lost, such as high cirrus clouds. So one might say, well, why don't we just measure the brightness of the host star? Well, if we're just measuring the brightness of the host star and we see a dip in the brightness of that star, we're not sure if it's due to a high passing cloud or if in fact it's due to an exoplanet transit. So what we do is we use comparison stars in the same field of view, measured at the same time as the host star, to be able to distinguish between, again, common events such as high clouds passing over, because theoretically a high cloud passing over is going to cause a dip in both the comparison star and the host star. Now, we measure the brightness of both the comparison stars and the host star using a technique called aperture photometry. And we'll see in a minute how this works, but aperture photometry compensates for background sky glow that might be due to things like light pollution, the moon, and so on. So aperture photometry around a given star computes more accurately the brightness of the star itself, taking away any counts of ADUs, for example, due to background sky glow. Now, once we've done the done aperture photometry on the comparison stars and the target star, then we compare the relative change in light between the host star and the comparison stars. And that method is called differential photometry for obvious reasons. It's measuring the difference in photons between the host star and any number of comparison stars. So a data point on the light curve then is the relative change in flux or brightness of the host star relative to the comparison stars. And once we have a number of data points on the light curve, we fit a model to it that represents a transit. And then based upon how well that model fits those data points, we can assess how good our observation is. Now, a little bit more about photometry, aperture photometry. If we take a look, we zoom in on, let's say, a star of interest. What we do is aperture photometry creates a aperture or a ring of a certain radius. In this case, it's 13 pixels around the star. We leave a little gap, and then we create this outer donut called an annulus. In this case, it begins at pixel 14 up to pixel 29, so it has a width of 16 pixels. And the way aperture photometry works, as sort of alluded to earlier, is we collect the amount of light per pixel in the background sky and subtract off that number per pixel from the values in the aperture, so that what we get is a more meaningful number of the brightness of the star itself. So that concludes module 4, and in the next module, we will be reviewing some of the online resources that are helpful in doing our exoplanet predictions.